Hi everyone, this is the demo of EE278 term project. I'm Mahesh and my partner is Preethi. We both together have implemented the view and illumination invariant image matching system using iterative SFIT. This basically involves in rotating of the image over a valid angle range so that the matching system is invariant of the view. We basically extract the feature points of the given two images and determine whether both of them match or not. Considering this for the demo purpose, we have implemented the image warping on the NIOS 2 processor, and image warping is one of the important techniques that we have used in the project of illumination of implementation of view and illumination invariant matching system. So let's start with the demo itself. So at the beginning, let's start creating a new project. So let's create a project called Final 6643. So let's keep the name of the project as Final 6643, and let's give the same name to the top level design entity of the project. So we don't have any files for now, so we are skipping this step. We need to take Cyclone 2 as a device family, pin count as 484, and speed grade as 7. So let's take this, select this device and select a Verilog HDL and finish. So let's start the QSys. So QSys is a system building software where we drag and drop the system components. In this we basically will bring together the NIOS 2 processor, on-chip memory, JTAG, UART and performance counter. So let's start with NIOS 2. So NIOS 2 processor. So normally there are 3 variants of the NIOS 2 processor, out of which we prefer the economic version, which is the one which I had selected. So let's bring on-chip memory. So by default it will be 4096 bytes. So but let's take 8192 bytes to be on the safe side, and let's bring in JTAG UART. And finally the performance counter. So if you see here, there is a default clock generator whose out we will be connecting the clock and the reset to each and every block present in this. So to on-chip memory, to JTAG UART, and to performance counter. Now we give the data master and instruction master to the on-chip memory, and we continue to give the data master input to the JTAG UART and the performance counter, and we need to connect the interrupt request. And if you see, there are couple of errors, bunch of errors, out of which few was like mentioning about base address. So let's go ahead and assign the base addresses. So we are left with two errors. So these are related to NIOS 2 processor. So let's reset the vector memory to on chip memory and exception vector as well and finish it. So the errors are gone. So let's save this, the name same as the one which we given at the beginning. So final 6643, and then we need to generate that. Basically this QC generates the files, Verilog files and .qip files that can be imported into the Cortex later. So currently it's generating the files. So there are no errors and warnings. Let's go ahead and close this. And now we need to assign the pins. First we need to add the files. So we'll go ahead and select the QIP file. So this basically represent the entire submodules which are there inside all the Verilog files of the submodules. So we are bringing in here. So we basically add that, and okay. So in the Cortex. So now we assign the pins of the FPGA. Here we only have the clock pin of the FPGA which is outside the block and which we need to connect. So let's name it as clock_clock. And we assign the location and IO standard. So let's say location is equal to pin underscore L1, and let's keep the IO standard as 3.3 low voltage TTL, and let's save it and compile it. So once this compilation is done, so the compilation was successful. So once this compilation is done, this generates SOF files. So let's go ahead and let's burn that SOF file into our DE1 board. So if you see, you can find the USB blaster over here. So we need to add that SOF file now. So it will be in the output file. So if you see, this is the final 6643 SOF file. So by the way, 6643 are the last two digits of me and my partner. So we have kept that name. So let's go ahead and select final 6643. So let's burn it, and you can see it's 100% successful. Let's save that as chain1 CFD file in the output file of the current project. So now let's start the NIOS 2 software build tools for Eclipse. So let's browse. So let's this would be the workspace for the Eclipse. So now we need to bring in NIOS 2 application and BSP for from template. And now this SOPC information file is nothing but it contains all the information about the system which the Eclipse need to program. So let's go ahead and bring in that file. So this is the SOPC info file. So now let's add the project name. So it will be final6643_NIOS. And we will be selecting the hello world small because like the hello world small will occupy, I mean like it has less memory footprint because we are using the on-chip memory which is quite small. So we need the program which will have less smaller memory footprint. So we'll go ahead with that. So so if you see, we have two folders, final66 NIOS which has the hello world program. So this is basically the basic program which is available. So which will print the hello from NIOS. So let's go ahead and do that. Let's build the project. So once that is done, so right now as we know that we already built the system on the board using the SOF file, so we can directly build that on the board. So for in order to do so, we'll be using this run as will be using run as NIOS hardware. So basically now we should be getting hello world hello from NIOS 2 printed on the console. Yeah, there you go. So let's instead of this hello from NIOS 2, let's change the program to our program, the image warping program. So let's save that and let's build the project. So we even have the performance counter to measure the number of cycles in it. So now we need to run it as NIOS 2 hardware. As you can see, it displays the total number of cycles consumed by the image warping technique, and we have the pixel values of pixel values over here. Basically what we are doing is so if you see, we have an image which is given as input to the MATLAB, and it generates the pixel equivalent matrix of the image, and we give that as input to the Verilog, and this is the input image, and this Verilog this C program will turn that image, rotate that image by 45 degrees or any fixed angular rotation. So once we do that, we'll get this output pixel values. So that would normally be equivalent to this given image. So we have taken the screenshot of the MATLAB program. So because like we have limited time available, so this is the output of our program. Thank you.